All right, welcome to this pre-lab video for the volumetric analysis pre-lab. This is the in-person lab for this week in Chem 105. Now, I understand most of you haven't had a whole lot of experience with this, and that's why we're going to walk through and do a little bit of this piece by piece, just to kind of give you enough of what you need to know to do the data collection and the calculations for the lab. So let's start with concentration. Now, we've seen the concentration of unit of molarity on a couple of different occasions. In the lab that we did last week, that series of chemical reactions lab, we looked at molarity in close proximity there when we were looking at the nitric acid. By definition, molarity for a substance is the moles of solute per liter of solution. So what that means is that if I have a solution that is 16 molar nitric acid, like we did in the copper lab, that means that there are 16 moles of nitric acid, HNO3, in every liter of the solution. And this kind of shakes down from there to looking at other things like masses. What is the mass of the solute? Well, we can look at it from the standpoint of, okay, well, volume times molarity times the molar mass would give us the mass of solute. So if I took that and kind of applied it and said, okay, well, if I only have 100 milliliters, which would be 0.1 liters, times 16 moles of nitric acid per liter of solution, and I multiplied that by the molar mass of nitric acid, which is 1.01 for hydrogen, 14.01 for nitrogen, and 16 times 3 for oxygen, I get 63.02 grams of nitric acid. So I take all of that, 16 times 63.02 times 0.1, and I would find I would need a little bit more than 100 grams of HNO3 to get this done. Now, this kind of calculation becomes important because if we were actually making solutions, this is how we would know how much stuff to add together to make the solution that we needed. Now, that's not really what we're going to be doing in this lab, but it plays a larger role in terms of what we'll ultimately be doing with labs of this type moving forward. And so to that end, what is the molarity of an aqueous solution prepared by taking 36.5 grams of barium chloride in enough water to make 750 milliliters of solution? Again, we're talking about molarity here. Molarity would be, in this case, moles of barium chloride, BaCl2, over liters of solution. And so what we need to do is we need to find the moles of barium chloride, which we don't know right now, and the liters of solution, which we can take by taking that 750 milliliters and dividing it by 1,000, which would give us 0.7500 liters of solution. So we've got the denominator figured out. We just need to figure out the numerator. For the numerator, we're going to need to do this conversion, 36.5 grams of barium chloride into moles. And for that, we need the molar mass of barium, 137.33, plus the mass of chlorine, 35.45, multiplied by 2. There are 208.23 grams of barium chloride in every mole of barium chloride. And so 36.5 divided by 208.23 to 3 significant figures would give me 0.175 moles of barium chloride, which I can now put up in the numerator of my fraction. And so 0.175 divided by 0.7500 to 3 significant figures would give me a molarity of 0.233 molar barium chloride. So that's the kind of calculation that we would want to do if we were trying to figure out the concentration of a solution just based off of raw materials, raw goods. But again, that's really not the point here. The reason I bring this up now is I know that there's a pre-lab question of this type, and I wanted to make sure that you had an ability to do it. The real point of this particular lab is the titration. Now, a titration is simply an analytical method. This is a way of doing precise quantitative analysis to help us determine the concentration of an unknown solution by reacting it with a solution that has a very, very well-known concentration. And so the substances in question here that we're going to be looking at this week, we will have a very, very well-known concentration of sodium hydroxide. This is what we are going to refer to as our standard solution. And with that standard solution, we are going to measure the concentration of a solute. The solute is going to be an unknown acid that is solid. And so we will make a solution of it. And the titration will help us determine the molarity of that solution, which we can then turn around using similar kinds of calculation techniques to what we just did to find the concentration of the unknown acid and use that to figure out the mass of the unknown acid and eventually its molar mass. Titrations work on the basis of something called the equivalence point. The equivalence point is when the number of moles of acid equal the number of moles of base. And so from that particular standpoint, they effectively cancel each other out. I won't say that they neutralize each other, although that does happen in some cases. Neutralization indicates that a pH of 7 has been reached. And in certain types of calculations of certain types of titrations, that is indeed what happens. But in other kinds of titrations, like the one that you're about to do, we don't actually neutralize the acid and base solutions. The resulting solution ends up having a basic pH because of the weak acid character of the substance that we are using. But equivalence points, well, they're kind of difficult to see. Take sodium hydroxide, for example. Sodium hydroxide is a clear and colorless solution. Most acids are also clear and colorless solutions. When they react with each other, they give clear and colorless solutions. So it can be really, really hard, even with really great precision techniques like titrations, to find the equivalence point. So we tend to focus on something else instead. We tend to focus on what we call an endpoint. Now, an endpoint and an equivalence point in a lot of ways are very, very similar. And in fact, from a volumetric standpoint, they're only off by a small amount, a couple of tenths of a milliliter at the most. But the advantage to the endpoint is that in an endpoint, we use an indicator. The indicator has a particular pH range in which it's going to change colors. And if we choose the right indicator, we end up getting to see the color change occurring very close to where the equivalence point is. And it gives us a pretty good estimate of what's going on and how we can ultimately use it. Now, the indicator that we are going to be using in the lab this week is one called phenolphthalein. This happens to undergo a pH transition from colorless to pink. This color transition takes place somewhere between pH 8 and 10. So at concentration or at pHs less than 8, we see the colorless version. At pHs greater than 10, we see it in a darker version. And in the range in between, we see kind of an intermediate rosy kind of color, where we do see some coloration, but it's not nearly as strongly pronounced as this. And that's ultimately what we're shooting for, is kind of that in-between zone there. Other indicators do exist. Methyl red has a particularly interesting kind of transition. It's more on the acidic end of the spectrum, so it helps with other kinds of titrations that we might encounter. But again, we're going to use phenolphthalein for the lab this week because it does what we need it to do and changes colors right around the time where we hit that equivalence point, at least within 1/10 of a milliliter, which is more than enough to help us to pretty accurately estimate what the concentration of that acid solution is. When it comes to doing the calculations, we're going to use a modified version of the dilution equation. Remember that the dilution equation we've used before, M1V1 is equal to M2V2. This allows us to take solutions that are at a high concentration, dilute them to a new volume, and figure out what the concentration is based upon that volume. Here, all that we're doing is we're modifying it with splitting it into an acid side and a base side, and adding a denominator that accounts for the balanced chemical equation. So if I have a simple chemical reaction like this, kind of your quintessential acid-base neutralization reaction, and this one is a neutralization reaction. We've got our base and our acid here, and the setup of this would be, I would have the molarity of the HCl multiplied by the volume of the HCl divided by 1, equaling the molarity of the sodium hydroxide multiplied by the volume of the sodium hydroxide, also divided by 1, because the stoichiometric coefficients in each of these cases are not printed here because they are 1. If this was a 2-to-1 ratio or a 3-to-1 ratio or a 3-to-2 ratio, that would be reflected in the denominators here. Now, the other important thing about this particular method is that our volumes here do not have to be liters or milliliters or whatever. So long as they are the same volume unit, this equation will work. Similarly for the concentrations. If the concentrations are the same on both sides, it doesn't matter if they're molarity, molality, percent, whatever the case may be. So long as they are the same, we'll be able to calculate correctly off of this equation. Now, most of the time, we don't care about any other calculation of concentration other than molarity, but it's nice to know that others could work if we were in a pinch. So let's take a look at a couple of examples. What is the concentration of sulfuric acid if 15 milliliters of it reacts with 18.45 milliliters of a 0.0973 molar sodium hydroxide solution? So the real trick here is we've got to start with a balanced chemical equation. Sulfuric acid reacts with sodium hydroxide to make sodium sulfate and water. Now, from the balancing standpoint, I'm going to recognize that I need 2 sodium hydroxides and 2 waters to make this balanced, which means that if I look at my equation, I'm going to have to make sure that I substitute the correct values in the right places to get this to be completely correct. And so my molarity of sulfuric acid is what I'm trying to find. My volume is the 15.00 milliliters that I was telling us about. The coefficient here is 1. On the flip side, my molarity of sodium hydroxide is 0.0973 molar. My value is 18.45 milliliters for the sodium hydroxide, and my coefficient is 2 here. Doing some algebra to solve, I'm going to need to multiply each side of the equation by 1 over 15 milliliters. That's going to cancel out everything. So my my ones cancel out here. My 15 milliliters cancel out. And nothing cancels out on this side other than the milliliters. So everything here is numeric other than the molarity, which means that my final unit here is going to be, well, molarity, mole. So when I do everything and I set it all up, what I end up getting is the molarity of H2SO4 is going to be 0.0973 multiplied by 18.45 divided by 2 divided by 15, which means that the molarity of the sulfuric acid to 3 significant figures, 0.0598 molar sulfuric acid. All right, let's do one more example. If it takes 21 milliliters, or excuse me, it takes 21.33 milliliters of our 0.1199 molar solution to reach the endpoint with 25 milliliters of the unknown HCl concentration, what is the concentration of the hydrochloric acid? Well, we've been given the balanced equation here already, so that part's all okay. We want the molarity of the HCl multiplied by the volume of HCl over 1, the coefficient of HCl, equal to the molarity of the NaOH multiplied by the volume of the NaOH divided by its coefficient, also 1. So this kind of distills down to just molarity times volume equals molarity times volume. Both the denominators are 1, they cancel out, it kind of works. So the molarity of the HCl, which we are trying to find, is equal to the volume, which was 25.00 milliliters, and that is equal to the molarity of the sodium hydroxide, 0.1199 molar, times its constant, or its volume, 21.33 milliliters. Since I have no denominator because they've canceled out, I just need to divide each side by the 25 milliliters. So the molarity of the HCl is equal to 0.1199 times 21.33 divided by 25 to 4 significant figures, 0.1023 molar hydrochloric acid. So that's how you do titration calculations. Now, before we completely go off here, let's take a look at the pre-lab that you're being asked to do this week. And from that standpoint, it kind of falls into the first 2 questions are very familiar. Question 1 is exactly like the kinds of questions that we were looking at in the first example that we did. We're going to take the grams of oxalic acid and turn it into moles. And then we're going to take that number of moles and divide it by the volume, which in this case would be 0.4500 liters. And that'll give us the molarity of the oxalic acid. So that part, not too bad. We can work with that, right? The second part is a little bit different, but not too bad. We've got 20 milliliters of oxalic acid and 22.63 milliliters of sodium hydroxide was the molarity. Well, we need the balanced equation. And this is not a 1-to-1 reaction, it's a 2-to-1 reaction. And so that is going to complicate things a little bit because now I've got numbers in the denominator. But aside from that, everything else kind of fits what we've been doing in the other examples. Now, the molarity of the oxalic acid, that is going to have to be substituted down here. So you can't do B until you do A. The only difference is that instead of finding the concentration of the acid, this time we're looking for the concentration of the base. And so it's going to affect how we do things a little bit differently here. The last part, this is actually mimicking what you're going to do in lab. Because in lab, you're going to try to find the molar mass of an acid. And to do that, you're going to use titration data. So luckily, the acid that you use reacts with sodium hydroxide in a 1-to-1 fashion. So that means that however many moles of NaOH there are, that is going to be the same as the number of the moles of acid. And so if I use this equation, what it is going to tell me is that from a standpoint of reaction, I'm going to take the molarity of the NaOH, multiply it by the volume that I use in the titration in liters, and that'll give me the number of moles of NaOH. Since it is a 1-to-1 ratio, as we just looked at here, that means it'll be the same as the number of moles of the acid. To find the molar mass, I need the mass of the acid divided by the moles of the acid. Mass of the acid's been given to us, 0.9174 grams. The moles we need to find, once we do, we'll be able to figure out the molar mass. So I'll give you more details about the actual procedure itself and what you have to do when we get to lab this week. But for now, that should help you a good deal with trying to figure out how to do the pre-lab calculations and solve the pre-lab that is due soon here. And so that's where we'll stop this particular video. If you have any questions, feel free to send me an email or drop me a text and remind. But I will see you next time in lab.